Hello everybody. Today we're gonna talk a little bit about numbers and how those numbers are represented in computers. Basically, what we have it's a positional notation. So we have digits in a number, and the position of this digit in the representation. It is important, and so usually what we have it's a base, a radix r with any positions. So for the position 0, it's we're gonna use the rightmost digit. So the least significant digit of our number will be the rightmost digit. And the position n-1, it will be the leftmost. It's the most significant position. You can see that, for example, if I have the number 123, the most significant bit would be the number 1 in the hundreds, and the least significant bit would be the 3 in the decimal part. So in the unit part, sorry. So if the position is important, we're gonna take the digit in that position and multiply by the radix to the power of the position to get their value, right? And we're gonna sum all those values. So the digit in that position times the radix times to the power of the position, and when we sum all of the digits, we have the value of the number. For example, we can have the base 2, and we always gonna look into which are the digits, what are the digits, what are the representations of the numbers that we're using, right? So in the base 10, because base 2, because we only have two options of digits, r-1, so we can represent all the digits that it's required for a base 2 with 0 and 1. If we're using decimal, so it's 10, so 0, 1, 2, and 3 to 9, but that could be expanded to any radix, any base that you want. And again, so the position determines the significance of that digit. For example, you have here 482, and to get the value of this, you just have to multiply the digit in that position times the 10 to the times the base, that's in this case is 10, to the power of that position, plus the second one into the second digit, that's in this case is 8 times the radix, that's 10, to the power of that position, that's 1, and plus the last digit times 10, the base, to the power of that position. We always use we start from 0. And so let's say we have a different type of bases. So let's say we have base 5. So we're gonna use digits from 0 to 4 to represent the numbers that we have. And we have the same process, and in the end of this process we're gonna have the value in the decimal system, the decimal base. So we have 4. This is the leftmost digit in the position number 2. That's third position, but it's the position number 2. We start 0, 1, and 2. So we multiply that digit 4 times the radix, that's 5 in this case, to the power of the position, in this case is 2. And we do the same for the next position, that's position 1 here. So the digit is 2 times 5 to the power of 1, plus the last digit, that's 1 times 5 to the power of the position, that's 0. And with this we know for sure that in base 10 that number is 111. And because of the nature of the modern computers, we only use we only store two values, right? Even if we move to another type of circuit, for example, if you want so we only store like two values, 0, 1 if there's electrical current, or if there's not electrical current. So we can represent our numbers only with zeros and ones, right? So we're gonna use the binary, the base 2, the radix 2, and we're gonna do the same process to identify which number we're talking about. So we have, let's say we have on the first digit we have number 1, we have digit 1, and the position starts with 0 again, 0, 1, 2, 0, 1, 2, 3, 4. So it's 1 times 2 to the power of 4. So it plus the next digit times 2 to the power of 3, that's the next position, plus 0 in this case, because our digit here in position 2 is 0, times 2 to the power of 2, plus 1 times 2 to the power of 1, in this case that's position number 1, and plus 0 to the times 2 to the power of 0, that's first position. It's gonna be easy to see that when it's 0, of course it's just 0 and 1. So when it's 0, we can just ignore in the final sum this position, and because it's easy to see that the position is always the same, because we're keeping the same basis. So it's easy to see that this position is always or 0 or 1, right? This position is always 0 or 2, 0 or 4, 0 or 8, 0 or 16. So at the end of the day, it's gonna be easier for you to see is just the position, and sum and include on your sum the numbers that you have ones, right? So this is 16 plus 8 plus 2, and it's 26 in base 10. So that's just an easy way to see the number in binary and know for sure which the value in base 10. Just like remember the positions. So it starts with 1, 2, 4, 8, 16, 32, 64. And where is 1, you just add this number up. Yeah. So the radix, you can see that the radix is chosen by convenience. For example, in the early days of computers, we tried, the engineers and the developers, they tried to use decimal systems, but it's really hard to split the voltage in 10 and keep that reliably. So it's easier to, below, let's say 0.1 volts, it's 0. Anything that's below that, it's 0. And if it's higher than, let's say 4.9 volts, it's 1. So it's a really big range, so you can keep track of that easily. And at the end of the day, you're gonna use like Boolean algebra and Boolean arithmetics. So that makes more sense to use Boolean. But that doesn't make but you choose the radix depending on your application. And computer systems usually use radix 2, 8, and 16 because they are easily converted between them. And especially the octal and the hexadecimal, the name of the 8 and 16 radix, they are a compact representation of the numbers because they use less bits to represent the same number. So in the online exercise notes, on the online notes, we're gonna see some exercise like this where you have a number of dots, and the idea is how to describe these red dots, the number that we have here, in base 2, 5, 10, depending on the exercise. So we already did that, but how do you convert this any radix to a decimal, right? Because at the end of the day, you need decimal numbers to do some math. You need decimal numbers to show your results of your computation. So how do you do that? The same way we did before to see the representation of that number. So for example, here we have 321 in base 4. Again, the digit in the position 2 is 3. So it's 3 times 4 to the power of 2, that position 2, plus 2, the next digit, times 4 to the power of the position 1, that's position here, plus 1, that's the last digit, times 4 to the power of 0. And you do the basic math, and this is 57 in base 10. I forgot to put the base here. And for example, you have we can have I can show you a really good there's a constructor, the integer constructor in Python, that you can use to convert from any base to decimal. So if you have, let's say the example here, 11 0 1 0 1 0. So in base 2, this is 54. If you want the base 6, it's possible. So it's 9,000 something, and you have base 9, for example, is 65,000, and that's it. So it's the integer constructor in Python you can use to convert any base actually to decimal. So yeah, in computers it's really common to see binary, octal, and hexadecimal. The binary base, as I said before, has the digits 0 and 1. The octal base is gonna have the radix minus 1 digit, so 0, 1, 2, 3, 4, up to 7. And the digits for hexadecimal should be 0 to 15, right? But to avoid confusion, in computers you're gonna use letters to represent from 10 to 15, because otherwise you're gonna have like 11 here. It's gonna be a mess, because sometimes you're not gonna you have the number, but you're not gonna split the number into the digit, so it's not clear if it's 11 or if it's 2, for example, in binary. So yeah, so you're gonna see a lot of you're gonna see the letters from A to F to represent 10 to 15 in hexadecimal. So as I said before, there's a direct relation between octal and binary. So one digit in octal, it's 3 digits in binary. So you can see it's 0, 1, 2, 3, 4. So that's the idea. You can represent the same number, but it's with a compact version of it. So yeah, any grouping of 3 binary digits can be converted into an octal. So you can see that I here have 7, and this is the binary representation for 7, and this is 3. The second digit here is 3 in the octal, and this is the representation of 3 in binary. So the same. So if I have 123 in octal, I can have 1, 2, and 3 in binary, and this represents the same. So it's really easy to convert from octal to binary. The same way here. So here we have 6210. Here we have 6 in binary. Here we have 2, 1, and 0 in binary. So that's how easy to convert the octal to binary. And the hexadecimal is the same. So you have the same number here. So you have 0, 1, 2, but in this case we're gonna group in 4 digits for binary, and we're gonna have the same representation in the hexadecimal. So AF here in hexadecimal, we have A here. Remember that A it's 10. So it's, for example, here this 4 bits, it's 10, 8 plus 2, and F, that's all 1, so it's 8 plus 4 plus 2 plus 1, this 15. So AF in hexadecimal, it's 10 here and 15 here in binary. So 1, 2, 3 is the same in hexadecimal. So we group 4 bits, it's 1, this 4 bits is 2, and this 4 bits is 3. So CAFE, CAFE. So this is the binary for C, that's actually 12. This is binary for A that we saw before here, so it's 10. And this is binary for F, that's 15, 8 plus 4 plus 2 plus 1. And this is binary for E, that is 8 plus 4, 12, and 14, sorry. So basically what we have, so it's to convert from decimal to binary, we can extract the least significant bit using the mod operand in a high level language, and just remove that last bit. So that's what we're doing here. Because when you're doing this, the conversion between a decimal number that's V to the binary, for example, you're doing a division here that you only cares by the rest, right? So the mod division is this, and we are including this on this string. So if we divide, for example, 3 divided by 2, it's 1, right? Plus there's a rest that's 1, and that's what we are saving here. So we're just saving the rest, and because it's binary, you're just saving the zeros and ones from this, because it's like the radix is 2. And this is what we're doing. We're just removing this division that we just did. And this algorithm that you use the mod for building the string, and we use the floor division to remove the last binary digit. We can use that for octal and for hexadecimal as well. So we just have to change this for 8 and for 16, and we're gonna have the same behavior. That's really interesting. But in the end, because we're doing that like in the opposite way, we have to reverse the string in the end, so we can have the correct string. But yeah, but these numbers has to go inside computers. So for example, if we have 8-bit computer, how are we gonna store that? So it's basically the same equation that we had before. So we have 0 to 8 minus 1, that we have 7 positions of bits, with the most significant bit being the 7, and the 7th bit, the position number 7, and the least significant bit being the position number 0. For example, we have here 0, 1, 1, 0, 0, 1, 1, 1. This is 103 in decimal. So this is how you're gonna represent numbers in the computer. So it's just a string of bits with the most significant bits. That's the important part, actually. So the most significant bit is to be your left, and the least significant bit is gonna be on the right. So the smallest 8-bit stored in a computer is the 8 bits with 0, and the largest 8-bit stored in a computer will be like 255, because we're using we start with 0, so all ones means that we have 255. But that's for unsigned integers, right? If we are gonna use if you're gonna use signed integers, would be a different range here for sure. So the range for an 8-bit unsigned integer is 0 to 2 to the power of 8 to the radix minus 1, because we start with 0, so 255. And you can see the difference when you have larger words of bits, larger. Your range is going to be really larger when you use 16 bits, for example. If it's unsigned, you go from 0 to 2 to the power of 16 minus 1 is 655,000. So for n-bit unsigned integer has a range of 0 to 2 to the power of n, of that size of your bits minus 1. But yeah, but we also have to work with signed numbers. We have to represent the positive, the negative, and the 0. Usually computers can use, usually you're gonna see 3 types. You can have the sign magnitude. Basically you use the first bit as as a indication. In all those three types, we're gonna use the first bit as the indicator of the negative, but we're gonna have those are three different representations of the negative number. For example, for sign magnitude, the only change is that we have, for example, 4 bits. We're gonna use the first bit, the most significant bit, for the sign, and the other 3 bits are the same number that we had before. So here's the modified equation. So you have the position 0 to, for example, in an 8-bit sign magnitude, we have 0 to 6 positions. But if the most significant bit is equals to 0, it's the same. So you just sum it up and it's your number. But if the sign the position 7 or the most significant bit is 1, it's a negative version of that number. So it's expected that you're gonna have half of your range now for positive and half of that for negative numbers, but it's still you're gonna have a really weird behavior, because you have like 2 zeros, right? You have the zeros where the 4 bits are zeros, and you also have a negative 0. That's weird, right? Because you have 1 followed by zeros, it's also a 0. And so if you have here with sign magnitude, this number, it starts with 0, so it's a positive number. It's just the number that we had before, so it's a 7 decimal. In this case, we have the first bit is 1, so we know that's the negative number, and the rest of the bits, the last 3 bits, is our actual number. So it's you just put the sign minus in front, so it's -1 in this case. Here we have the sign again, so it's a negative number, but and the rest is we can compute the decimal representation, so it's 16 plus 8, so it's 24 plus 1, 25, so it's -25. But here we have a really weird problem, because this, for example, if I have -1 in this case, and +1 should be 0, right? But if we sum this up, the result's gonna be -2, because this one plus 1 here, it's gonna be 1, and the sign bit it's add up with 1 with 0 here. So in the end, we're gonna have a -2. So if you're using sign magnitude, we need special logic and a special, let's say, a subtraction unit to do this operation. It's not a problem, but when you have electrical components like digital logic components and gates, you always try to reduce the number of gates that you need. So if I have a representation of numbers that I can just use a regular addition to do the subtraction, because it's just this is an addition, right? The operation here is addition, is not subtraction. It's just because one of the numbers it's negative. It's better, right? So for that, it's kind of what we want, but not really. So with 1's complement, basically we also use the first bit as a sign bit, but we invert all the other bits. So all this equation here is just to show that the representation of this, it's basically you have to get the decimal version of this. I'm going to simplify for you. So the decimal representation of this, for example, the negative number, it's you invert all the bits and you add 1 to the last one. So in this case, you can see that the first digit is 0, so it's a positive number, so it's number 2. In this case, you can see that it's a negative number. You just invert all the bits and you have the number 7. And in this case again, so you have it's a negative number. When you invert all the bits, you're gonna have 5. But again, in this case we can add for example -1. This is the representation of -1. If you invert all the bits, you have 1. And you can add this plus this, and you're gonna have like a different type of 0, because it's all ones. But we know that if we invert this, because it's a negative number, it's gonna be 0, all zeros. So again, in this case we can use this operation to and actually we're gonna need to do another operation after this to have the actual result. I'm gonna show in a couple of slides, because this will not give you the correct answer for all the operations that you want, but in this case it actually works. But in most cases you have to add 1 here to get the correct result. But okay, but in this case we don't need a special logic or a special subtraction unit to do the operations, but we still need to do some extra operations to get the correct result. And we still have the 2 zeros that we actually don't want because it's confusing. And to solve those questions and to have a good representation, we have the 2's complement of the decimal value. And if we do all this operation here, we're gonna see so we have 1 0 1 1. This is the representation of -5 if you follow the equation here. But basically the easier way to do that is that you apply the 1's complement. Basically you invert the number, you add 1, and when you do the opposite operation, so you invert again and you add 1, you go back to the number that you want. So if you need the negative version of a number, you do this operation, you invert and you add 1, and you have that number. But the good part is that we don't need to do any other operation. We only need to do this operation if you want to know what's the number in like if you want to negate the number, so to have the inversion of the number. But if we're doing operations, with this representation we don't need any extra logic or any extra operation. So negating a number, what I was saying, so if you have to invert the signal of the number, with the signal with the sign magnitude you flip the bit, so it's easy to do that. With the 1's complement we invert all the bits, that's also pretty easy. And the problem is with the 2's complement is that you have to do the 1's complement, so you have to invert all the bits, but you have to do +1 if you want to change the signal of that number, right? But let's see some operations here. So if we are doing some additions, right? So for example, if I want to do 5 plus -1, should be equals to 4, right? So we have here the sign magnitude, so we have 5 here, we have -1, but if you do this operation, it's gonna be a little different, right? It's gonna be 2 and this guy is gonna be 1 1, so it's gonna be -4 or something. Yeah, so I'm just trying to remember from but basically what you're gonna need is a special unit here, an extra subtraction unit, so you can have your 4 here. With 1's complement you don't need an extra subtraction unit, so you can have your operation here. So you have the you have the 5 here, and you have the -1, so it's 1, but all bits is inverted, so it's -1. And if you sum this up, you're gonna have like 1 1, in this case 2 0 1, so you're gonna have this, that's 3. But in every operation that you have with 1's complement, you have to add 1, and in this case you have your correct answer. In the case of 2's complement, you don't have this. So when you're having when you have the negated version, the minus version of the number, you already have added this. So it's just a matter of doing the addition, and you have the number. So no extra operation, no extra unit like a subtraction unit. And that's it for today. Thank you.